Hi everybody. In this video we are going to work on converting between regular XY rectangular Cartesian coordinates and our theta polar coordinates. So basically giving a point on a grid two different names. So let's actually start with that. We're going to draw kind of just a generic grid here. We're going to plot a generic point and give it two different names. We're going to call it both XY. And actually, let's start with that and just draw what X and Y look like. Now, if you're plotting a regular Cartesian rectangular point, we're going to start at the origin. We're going to go right X units and up. I'm going to put a right angle in there because that's perfectly vertical. Up Y units. Now, if I also call that same point R theta, that means to get, again, to this point, I would rotate theta degrees and travel r units in that direction. So this is theta. There's r. That should be a very familiar looking diagram. We've worked with the same diagram quite a bit, but we're going to pull some info out of here. Again, nothing really new, but just use it in a way we haven't before. So what we're going to try to do is see how basically these four symbols, x, y, r, and theta, are all related to each other. So we're going to try to write some equations that tie them in, that have maybe both x and r, or y and theta. Pull them all in together. The first one that I notice, and ideally you're kind of thinking through some options on your own here, but this is a video, so we'll do the best we can, is based on the Pythagorean theorem. Shouldn't it be true that x squared plus y squared equals r squared? Or let's just vary that slightly. If I just want to know what r is, I could take the square root of both sides. I'm not putting plus or minus because if you recall in this scenario, and that's just a distance, r is always positive, like the hypotenuse is always positive, so we'll just work with that one. Yes, I know we can plot points with negative r values, but in this case, this is going to be sufficient for us. So these are sort of two equations that will let us switch back and forth between Cartesian. If you notice, the left-hand side of both of those just has x and y. That's the Cartesian variables. The other side has r, that's polar, so that's going to let us switch back and forth between them. Now, we haven't done anything with theta yet. We've got a right triangle with an angle and some sides. Let's think about SOHCAHTOA for a second and see how we can pull theta into this. If I look at, let's say, for instance, sine of theta. Sine of theta would be opposite over hypotenuse. That would look like this, y over r. Now that right-hand side I don't love because we've got a mixture of Cartesian and polar letters. Think about it that way. So I'm going to move that r to the other side just by multiplying by it. So let's just vary this slightly here. I'm going to say r times sine of theta is equal to y. Now we have separated. One side is polar, one side is Cartesian. That's going to help us convert these coordinates and equations eventually. Can you try the same thing before I do with cosine? I'm going to write it up here kind of silently. Take a peek when you're ready. How's that look? X is the same as r times cosine of theta. Now, let's use that to convert some points back and forth between Cartesian and polar, and then vice versa. We'll go both directions here. So let's do a couple like the ones we're used to, regular XY Cartesian points, and we'll convert them to their equivalent polar form. Like just give them a different name, but they were going to end up in the same spot. Okay, so let's start with 2, 5. If I were to plot that point, and I go over 2 and up 5, right here, basically going to draw that same exact diagram. This is 2, this is 5. That's the Cartesian version of this. But what we're going to switch it to is, well, what are the r and the theta that go along with that? So here's r, here's theta. R, there's a couple ways you could do this. I like Pythagorean theorem for this one. Let's just do a quick Pythagorean theorem. A squared plus b squared equals c squared, or this will look like 2 squared plus 5 squared equals equals r squared, or what is this? 4 plus 25 equals r squared. Don't forget to take a square root of that. I'm going to leave it exactly as the square root of 29. It's 5 point something, but let's just keep them nice and exact. Now, to find the angle, how do we always find an angle? We use an inverse trig ratio, right? Now, you could technically use that square root of 29, but remember, best practice, like problem solving technique would be, don't use numbers you created if you don't have to. So if I look at the numbers that are already on there, I've got, with respect to theta, I've got an opposite and an adjacent, which means I can use tangent to figure out what theta is. So I'm going to say, okay, let's start here. Tangent of theta would be opposite over adjacent, so 5 halves. So theta is just, I don't need arctan here. I'm just in quadrant 1. We can pull that in later if we need to, but I'm just going to take inverse tangent of 5 halves right in the calculator. That angle is about 68 degrees, 68.2 degrees. Okay, so let's put this all together. Let's write an actual coordinate here. The polar coordinates of this point are, remember, r first, then theta. So square root of 29, or 5 point, whatever it is, you can put that there, and about 68.2 degrees. Whether I use 2, 5 or this new polar form of the coordinate, it would land me in the same exact location on that grid. Let's try another one. I'm going to plot this guy, negative 2 root 3 and 2. So negative 2 root 3, I'm going to the left and up. Okay, so I have something that looks like this, negative 2 root 3 and 2. I'm going to try to find r. How long is this? I guess I have the whole triangle in there already. And theta is always in standard position, starting at 0 and working our way around. Okay, so just watch when we write our final answer, we want it to look like that. I don't know if those numbers stand out as special numbers to you. If they don't, guess what? Use the exact same method that we did. You'll get the right answer. But this is maybe even a little bit easier. If that square root of 3 stands out as like, oh, that's from a special right triangle, that's a 1, 2 square root of 3 situation, where across from the square root of 3, if you remember, that is always 60 degrees. So this is just a 30, 60, 90. Which means instead of, now notice, instead of 1, 2 square root of 3, we've got 2 and 2 root 3, so we're going to double this. So that means we also have to double the hypotenuse. That radius is just 4. Let me draw here what, I should maybe draw the reference one. So we've got 30, 60. We're used to kind of this standard one, 1, 2 square root of 3. Notice what we have is just twice as big. Negative 2 is in there because we went left. And then if you have the reference angle in there, guess how big theta is? Let's just do 180 minus that. That angle is 150. So our r theta is just 4, 150 degrees. Whether I plot that or the given Cartesian point, I would land in the same spot on the grid. Do you want to maybe pause here and try the next one on your own? Start it back up when you're ready. Did you pause and try it? Let's see. Let me give you the answer and then I'll go through it. So if you tried that, it should be 6, 315. Or if you called it negative 45, that's also fine. So let's work that out. So 3 root 2 and then negative 3 root 2. I'm noticing already, oh, those are congruent. This is a 45, 45, 90. I'm going to throw that in there right away. What I want to find is how long is this side and what is theta in standard position. Now, you could definitely call that negative 45. You could just use that as the angle. You can't call it regular positive 45 because that should have been in quadrant 1 then. Now, regular 45, 45, 90, let me draw it kind of in the same position here, would be 1, 1 square root of 2. This is just, oh, you know what? I didn't even notice this. It's not just 3 times bigger. It's 3 times the square root of 2 times bigger. But the relationship between leg and hypotenuse is literally just multiply by the square root of 2. So I'm going to take either one of those legs and just multiply by the square root of 2. So that r, let me write it over here so I have some room, is take the leg times another square root of 2. Notice this doesn't like fit the mold very well. The square root is not where we're used to seeing it. That doesn't mean there's anything wrong with it. It's just we got to work a little bit harder for it. So if we multiply this, this is now a 3 times just 2. Root 2 times root 2 is square root of 4, or plain old 2. So that's 6. Again, you could still, if you're not certain about that, or you could always still use the Pythagorean theorem. You'll get 6 that way as well. Okay. Again, if I didn't make this clear, let's put our theta value up there as well. From standard position or in standard position, that's 315. Here's the polar coordinate. Now let's go the other way. This time we have r and theta. We are going to try to figure out the x and the y to go along with it. So let's plot this guy first at 573 degrees. I'm going to go 73. I'm going to call that 5 units. I'm going to draw my triangle because what I want are these two sides, x and y. Now, you could use some like SOHCAHTOA, let's find some missing pieces, but let me go back a second here. Remember these equations we wrote down over here? X is r times cosine of theta. If you have r and theta, you can literally just plug them in. It'll spit out the x for you. Remember, it comes from this. Like you could set this up and think, oh, I'm going to solve for x, but we already did that. We already solved for x, so just use it. So here's my two equations. I've got x equals r times cosine of theta. Y equals r times sine of theta. Let's just plug in 5 and 73. So 5 times cosine of 73 degrees, right, in the calculator. Make sure I didn't say this, but I assume you're in degree mode. Yes, we're talking triangles again. This is 1.46, about units. And then y would be just same thing, but switch to sine. So 5 times sine of 73, you get approximately 4.78. Okay, so if we were to plot that, look what that is. Like we'd go over 1.46 and up 4.78. Let me write that as a big coordinate. Here's my final answer up here. Okay, that's the Cartesian form of this given polar coordinate. Again, they land you in the same spot on the grid. Oops. Oh. Okay, let's try another one now. 150 or negative 150 is kind of special. So you could use the same exact method that we just did. Unless it says give exact values, then you might run into some trouble. So let's look at this guy. Okay, so 2, negative 150. Negative 150 is here. We're going to call that length 2. We want the x and y to go along with that. Now, yes, you could use those same exact equations. It would spit out your x and your y, but you're not going to get an exact value on one of these, okay? So here's what maybe we notice. This angle, this reference angle is 30. This is a 30, 60, 90. And this is actually, look right up here. Do you see it? We still have our general one written up there. The hypotenuse is 2. On the normal one we're used to using, well, guess what? It's also 2 here. So this is just a 1, 2 square root of 3 situation. Just make sure you get the numbers in the right spot. And we're going negative in both directions here. So y, this is the short side across from the 30, is negative 1. X is also negative because I went to the left. That's across from the 60. That's negative square root of 3. So let's put that together. That's my x and y right there. Negative 1. Nope, I got those switched. X first. Negative root 3, comma, negative 1. Okay, and then this one's kind of goofy. Let's see what this looks like. 180. So over here, but then r is negative 3. Remember what that means? We're actually going to head this way in the total opposite direction, 3 units. So I'm really going to go 1, 2, 3 units this way. We don't need a triangle for this. If you looked at that and I said, normally, tell me what its coordinates are. Wouldn't you just write this? Over 3, up, none. The funny thing is that's not 0 degrees, although it could also be 0 degrees. That's x equals 3, y equals 0. Okay, so just kind of a unique case. So just take a look at some of these because some are special right triangles. I could imagine those being like no calculator questions. Find exact values where those square roots come in. Otherwise, make use of those equations that we have. Make use of kind of Pythagorean theorem, SOHCAHTOA stuff that you know to find those missing measures. You should, while this is fresh in your mind, or the next stage in the packet here is just to do some practice. Okay, thanks everybody.